So to begin this note, we are going to be talking about some critical points. We know by now that critical points are where the derivative is equal to 0. I have given you a quick little graph right here, and we're going to take a look at it, and we're going to try and pick out some of this information. So we're going to be talking about some local max, some local mins, absolute max, absolute mins, and points of inflection. Points of inflection are a little bit harder to see, so we might pause for a little bit there. All right, so the first thing that we're going to do is we're going to look for some local max and local mins. Now remember, the difference between local max and absolute max. Absolute max is the absolute highest this graph will get, and a local max would just be still a maximum point, so, or even a local min, like still that peak or that valley, just not the absolute highest or the absolute lowest. So when I look here, I do see that I have a local min. Now I know that this is a local min and not an absolute min because this graph does go down forever. It will go down towards negative infinity. Now I can see that I do also have a local max right here. So this is a peak, but it's not the highest that the graph will get. And that means that this max right here is going to be an absolute max. So again, no absolute min because this graph will go down to negative infinity, but there's the rest of those. So the next thing that we're going to be talking about is a point of inflection. So there's a couple new terms that you're going to be learning about right here. So when I look at this local min, I can see that I have this U shape. And when I look at any of my maxes, my absolute max or my local max, I can see this kind of N shape. Now, what we're going to refer to these is concave up and concave down. So my N shape is my concave down. You can think about it like it looks kind of like a parabola facing down. And this U shape right here is going to be my concave up. So what a point of inflection is that point where on our graph it changes from concave up to concave down or concave down to concave up. So I do know that I am going to have some. There's going to be one here and one here. It's not really possible to see on this graph where they are, and so we are going to have to use some derivatives to find them. But I do know that based on this picture, they do exist. All right, so first derivative test for critical points. Always, always, always do the derivative first. I know that you've probably heard me say that multiple times. If you don't know what to do, you've been doing the derivative, you're always going to do that first in these questions. And please make sure that you're following all of the rules that we've already talked about when you're finding this derivative, because these questions are so involved. If you're doing the derivative wrong, everything else that follows will also be wrong. And of course I would go back and I would figure out where you made your mistake and give you marks, but the numbers probably won't work out and it will make your life a whole lot harder. So please make sure that you're taking your time with that derivative. So the first point on this page we have already talked about. So we know that if the derivative, f prime of a, is equal to 0, then f of a is a critical point. So once we get those zeros from the derivative, we plug it back into the original function and we're able to find that critical point. The next couple of points I know probably seem a little bit confusing, but if you really stop and think about what's happening, they'll probably make sense. I have a little, I guess, graph or sketch drawn in the top corner that might help you as well. So the first one says, if f prime of x is greater than 0 for some x less than a. So remember, a was that critical point that we were talking about earlier. So if we have a derivative of our x, when we plug in x, x is less than a, so x is going to be somewhere to the left of a, and it's greater than 0. It's positive, so that would represent, I'll use green, that would represent this increase right here. And the derivative is less than 0 for an x bigger than a. So now we're going to have an x to the right of a, and then we see a negative derivative that represents a maximum. Now, the second point says the exact opposite. So we're going to have another a right here. If the derivative is less than 0 for some x that is less than a, so our x will be here, we have a negative derivative. And if the derivative is greater than 0 for an x that is bigger than a, so our x is now to the right of a, and we get a positive derivative, that represents a local minimum. If the derivative is less than 0 or greater than 0 on both sides of x equals a, then f of x has a point of inflection. And again, we're going to be focusing on these later. I did just want to throw this in there just so that you can think about what is happening. I decided to go back and talk about point of inflection just a little bit more. I think that looking at a cubic function is going to be the easiest way for me to explain what a point of inflection is without really getting into what a point of inflection is. So just so you know, I will often say POI if I'm talking about a point of inflection. I am just going to start here. I'll use blue. We know that this is a cubic function, so y equals x cubed. Obviously, if we're taking the derivative, we're getting 3x squared. If I set that derivative equal to 0, which is what I need to do to find these critical points, I could see that I have this critical point at x equals 0. So typically, in our example so far, all of our critical points have been local mins or local maxes. What we're going to notice in this critical point is that it is actually a point of inflection instead. And when I look at this graph a little bit more, this last point above might make a little bit more sense. So before this point of inflection, or before this critical point at 0, I have an increasing function. I know that if I plugged in something less than 0 to my derivative, I'm going to get a positive number. At 0, it becomes a little less increasing, okay? After 0, if I plug in something bigger than 0, so 1, 2, doesn't matter, I'm still going to get an increasing function. If I plug that in, my derivative is still going to be positive. So instead of like with a max where it went from increasing to decreasing, or with a min where it went from decreasing to increasing, this point of inflection is increasing the entire time. And that's really how you're going to be able to tell when a point of inflection is happening. And then again, I did mention concavity a little bit. We are going to get into it a little bit more, but if I take a look at this, I could see that I have concave down. So this is half of my U shape. And then after 0, I do have concave up. Again, half of my U shape. I'm sorry, I should have said half of my N shape for before 0. So since I have a concave down and it is changing to a concave up, I do see that point of inflection as well.